Okay, in this video I want to talk about how would you show that a set, specifically an infinite set, is orthogonal. We said in the last video that to show it's orthogonal you have to show that every pair of them have inner product 0, meaning their definite integral is 0. That's actually going to pose some problems for us because the integral of 1 times cosine is going to look very different than the integral of a cosine times another cosine. So if I'm going to try and show that any pair of them have inner product is 0, I'm going to have to be a little strategic in how I do that. So first of all, let's get some notation out of the way. This 1, I'm going to call that my phi 0, and then I'm going to think about cosine 1x, cosine 2x, and so on as being phi n. For some n, n equals 1, 2, and so on. So these are my two groups of functions. We have the single function 1 and this long set of different cosines. Okay, so let's start off with, why don't we try and knock out infinitely many of the inner products at once. That sounds efficient. Let's try 1 with any one of these guys. So let's try the inner product phi 0 with any phi n. And so that'll be 1 with cosine, 1 with cosine 2x, 1 with cosine 3x, and so on, all at the same time. And so our definition was inner product is the definite integral from a to b, which for us is minus pi to pi, of the two functions multiplied together. And so let's sub in what are those functions actually. Phi 0 is the function 1. And phi n is cosine nx. And so really we're doing a definite integral of cosine nx, which we can do. That should be 1 over n sine nx, evaluated from negative pi to pi. And so when we plug in the limits, we have 1 over n sine n pi minus 1 over n sine n minus pi. But if you think about it, sine of a multiple of pi should be 0, and sine of a negative multiple of pi should also be 0, and so the whole thing ends up being 0. Wonderful. We want that to happen. We want to have the inner product is 0 so that these two functions, 1 with cosine nx, are orthogonal. Okay, but I'm not done yet because I still have to show that cosine x and cosine 2x are orthogonal. I have to show that cosine x and cosine 3x are orthogonal. I have to show that cosine 2x and cosine 11x are orthogonal. Again, I'm going to try and knock out as many of these at the same time as I can. So I'm going to try the inner product of phi n with phi m. And so I'm going to make an assumption that n and m are not the same, because I don't need to show that something is orthogonal to itself. Again, if you're thinking about it as orthogonal as meaning essentially perpendicular, it's a function or a vector isn't going to be perpendicular to itself. So no, this probably isn't going to work if n and m are the same. But if we have n and m are two different numbers, I don't know. We'll see what happens. So again, it's the definite integral of the product of these two. So phi n of x times phi m of x dx. And let's substitute what these are. Phi n is cosine nx. Phi m is cosine mx. Okay, and so we think back to some calculus strategies on how to integrate functions, and basically we don't like integrating cosines or trig functions with different angles, so I have to do something with that. It turns out though there's a trig formula that says a cosine times cosine can be written as a sum of trig functions in the following way. Cosine m, let's see. Okay, so a cosine times cosine ends up being written as a sum. I have off screen my formula sheet written down, but I accidentally copied it wrong on the formula sheet. So I wanted to make sure I have this right. Yeah, I think that's right. So we add the two and we subtract the two angles. Okay, so now we have a function that we can actually integrate. I maybe should have rewritten this as m plus n times x and m minus n times x. So it's a little easier to see what the integral is going to be. It's actually going to be the same as this integral up here where you just divide by the coefficients. So 1 over m plus n sine m plus nx plus 1 over m minus n sine m minus n x. And again, we evaluate from negative pi to pi. So I'm not going to stress too much about where this trig identity came from. If you want to look it up, they're going to be in any trig book. They're going to be in Google. Just look for product to sum trig formulas. So product to sum. Okay, anyway, if we plug in the limits, I'm not actually going to do that. I'm just going to let you use your imagination. If we have sine, m plus n are both whole numbers. When we multiply them by pi, or negative pi, we're going to have sine of a multiple of pi, which is going to be a 0. Same thing is going to happen over here. So I'm going to put equals ... and we do get a 0. And so if you look back at our two cases that we showed that 1 with any cosine ends up being orthogonal, and we showed that any cosine with any other cosine ends up being 0. Okay, yeah, so again, a large part of it is just going to be coming up with a strategy of how do I make sure that I get every case of every one of these functions with every other one without actually writing down infinitely many different integrals. In this case, we needed 2 groups to get them all done. If we had only done this one, we would have only shown that cosines times cosines end up being orthogonal. We wouldn't have actually showed 1s with cosines because 1 with cosine is a slightly different integral.